Hello, can you see the screen?
Yes, sir.
Yes, sir.
Okay. So this class will be the continuation of the scheduling algorithms. We have discussed in our last class some of the algorithms that possibly can be used for short-term CPU scheduling. What we found is the problem of scheduling occurs in many cases in the operating system. The least frequently uh, considered case is long-term scheduling, to which decides if a willing process can be actually created, if a newly incoming process can be actually created by allocating space in the process table or uh, initiating it in the system. Now this is almost not a problem in today's context because instead of process table we maintain doubly linked list, which can accommodate enough number of entries till you have got sufficient RAM, and the RAM also is pretty much available, the size of the RAM. So the long term scheduling these days, the problem can be ignored. The medium term scheduling occurs when a process need to be swapped out from the primary memory to the secondary memory and vice versa. So because it is related to memory management, this issue is dealt in more details in the memory management. The term may not be used as scheduling, but after all, the page faults and the on demand paging and all this in a broad sense deals with this scheduling issue, because we know that in a virtual memory management system, parts of the program or the pages of a program, some of the pages of the program may be there in the RAM. It's not required that all the entire process need to be in the RAM. Okay, so that is another issue. But in this particular process management topic, generally we are interested in uh, finding out the algorithms which can be used for assigning for picking up a process from the ready queue or in the preempted state to be assigned CPU. So what we found that these are the different performance parameters. Some of them they are user's perspective, some of them they are from the system's perspective, and they might be contradictory at times. These are the different possible strategies. We have talked about the first four of them: FCFS, SPN, SRT, and HRRN. And accepting FCFS, because FCFS is very trivial, we just keep on adding the new processes in the rear of the queue and pick up the process from the front of the queue. There is absolutely no decision related issues here, but the rest of it, as we have discussed, the SPN, SRT, or HRRN, these three rely on uh, or they expect as an input the service time or the amount of CPU time that the process will require. And as we found, and it is quite practical to understand that this may not be available. Okay, for a CPU bound process it is very difficult because it depends on the inputs that you give, and the user can provide the inputs, different inputs at different times. This is one point. In case of a IO bound process also, at different time steps when the process is willing to use the CPU burst, these may not be all the equal. Okay, sometimes it may be small, so very small time unit, sometimes it may be a bit larger time unit. So estimating these time is the service time requirement in terms of bursts of CPUs or in a single shot whatever, it's very difficult. But these three of these techniques that we explained in the table, as we found that we provide the service time information prior, and based on that the strategies are designed. Okay, so this is so in such sense these three algorithms are maybe sometimes better than FCFS, better performing, but they may not be actually implementable in the real scenario in a operating system design. That's why in this class mostly we'll be talking about some of the variants of or some of the scheduling algorithms which can be actually implemented without this impractical of the knowledge of service. Okay, so that will be the main focus. So we'll be talking about round robin, multi-level queue, multi-level feedback queue, and finally the fair share scheduling, which is actually used in the Linux based systems. So this FCFS, we found that it suffers from the convoy effect. So let me just quickly browse through the and we found that there's a lot of often it is found. The SPN or SJF. So what we found is basically there are two parameters to consider, input parameters to consider in a scheduling algorithm. One is the service time that is required, the CPU time required by this process, and another is the uh, waiting time, because it may have to wait for several units of time. So this together can play a role to find out who will be the next. And in SPN or SJF, we just basically rely on the service time. So based on the service time, these processes are scheduled, but this is of non-preemptive nature. That's the only thing. So this creates some problem because sometimes short processes need to starve. So the solution is, can we allow preemption of long processes when short processes arrive? That was the basic idea which triggered the next algorithm. So that is basically the preemptive version of this SPN or SJF, shortest process next. Some are waiting in the lobby. I think all are. Okay. Can you see the screen?
Yes, sir.
Hello?
Yes, sir. Yes, sir.
Okay. I got distracted because I found that somebody was waiting in the waiting room. Okay.
So
Anyway.
we can also accept the lobby people.
Okay, okay, then it's fine. I thought that I need to accept it. Fine. So the solution is, so if we can allow preemption, so the at least the short processes will not have to starve or will not have to wait too long. It requires small CPU, so it should not wait too long. So the immediate modification can be of the preemptive version of this. And if you can look carefully, so this preemptive version of this, that is shortest remaining time, is probably the most ideal kind of algorithm which can provide the optimal performance, because any process comes, or if you know all the processes that are in the system which is having the shortest remaining time, definitely it will be scheduled. But at the same time, during its execution, if some other process comes with a shorter time requirement, so definitely it will be preempted and that will be given the chance. So if we can do that, definitely the normalized turnaround time, that is your turnaround time, which is with respect to your waiting time, will be the minimum, okay, for all the processes. So this probably can be the best possible performance this can provide, or we can say it's optimal performance. So this takes into account the remaining service time. So this also has got problems like we cannot estimate the service time requirement, the service time that is there properly, but we can have some mechanisms to you know find out the possible values, I mean from the previous history, that also we have discussed. So basically we can consider a series of the last time steps, the last service times, assuming that the process is a IO bound process, so it has used CPU multiple times earlier also. So based on that we try to expect that if I schedule it next, how much time it is going to consume. But for a CPU bound process you don't have any idea because it just uses CPU in one burst. So this is one problem. And at the same time, the basic drawback of this technique is it is not able to consider the waiting time. Okay, so if a process is waiting for long, no matter its service time, so even if a, say for example, a CPU bound process which has got a very large service time, but if it is waiting for long because of a constant flow of short processes, then there is no way of elevating that its priority. So starvation of long processes cannot be overcome. So definitely the next possible change that we can think of is in terms of highest response ratio into account both the service time and the wait time. Okay, so this is what we found, the response ratio. As you can see here, this is the service time and the wait time both taken together, and this should be, so this is the highest response ratio next, and the technique was, the decision was the process with the highest ratio will be selected next. So we gradually found that the mean value of the turnaround time and the normalized turnaround time, it was better compared to FCFS if we consider the service time and the waiting time and all this. But we cannot bypass the estimation of the service time by any means in any of these three processes. And FCFS is definitely, it's a very, we don't consider it to be a probable implementation in a operating system. So the thing is, now the question is, we want to take into consideration the service time and also the waiting time, but we don't want to compute it explicitly or estimate it explicitly. So how can this be possible? How can we bypass the computation and still take the advantage of that? So let us see the round robin strategy, which we discussed during the introductory classes. So it is very simple. So we just have the, it's a queue of processes, and this is a CPU, and this is a process A, this is process B, and process C, and so here. And when A gets scheduled, there is a concept of time slice or time quantum in this case. So this is preemptive, and the preemption occurs uh, because of two reasons. I mean, or the scheduling algorithm is executed if a process terminates voluntarily, or even if the timer or the time quantum expires. So there is a single queue. So a particular process, if it gets a CPU, it can use the CPU for a maximum amount of time that is specified in the time quantum. After that, if it is not terminating, so this A will join the back of the rear of the queue. So A again comes and joins, and then the B gets scheduled. If B goes out, and then C joins this. So this is a pretty simple strategy, and you can see that if there are n number of processes waiting here in this case, and if the time quantum is q, so the any process will have to wait, no matter what type of process it is, it will be n minus 1 times q, because assuming that it has got the CPU just in the last step. Now when its turn will come after exactly n minus 1 into q time units. And the point is, this is same for all the processes. Even if you have a mix of CPU bound and IO bound jobs, each of them, they will suffer the same kind of delay, or they have to wait the same amount of time before they get the next turn. That's the point. But definitely a IO bound job will take fewer turns, or a short process will take fewer turns, and the long process or CPU bound process will take multiple turns. So the thing is, overall turnaround time will accordingly will depend on the total service time or total service requirement. Now the tricky part, so first of all, in this case you don't have to actually assess the service time requirement, so it automatically it's taken care of by multiple times it competes. But the critical issue is the size of the is the choice of the queue. What will be the choice of the queue? If the queue is too small, then the too large, that means a process will almost it can continue till the end. So that means it will purely be a kind of FIFO kind type of algorithm. So this RR will actually behave like a FIFO, almost like a FIFO. But if the queue is very small, then it is easy to understand that there will be too much of context switching and very little CPU execution, I mean actual execution, process execution. So that will be again is of no use. There will be a huge lot of wastage in merely switching the processes. So this choice of queue is definitely tricky, although we can avoid computation of service time that we need to do in the previous three algorithms that we discussed. And as we can see here that if the time quantum is 12, say for example, typically large, a process whose service requirement is set 10, it just there is no context switch that is required, it just continuously executes the CPU. If the time quantum is reduced to half, like say 6, then definitely after 6 units it needs a context switch, so there will be one context switch required in between the execution for this process of units 10 units requirement. But if the time quantum is 1, then there will be 9 context switches required, and each will be adding some kind of overhead. So this is the issue. So the main point is the choice of queue is obviously tricky and as well as non-trivial, and that will affect severely the performance of the system. And this example can show us that how and in what way it impacts. Okay, so we'll take the same example of 5 processes A, B, C, D, E, and these are the Turner arrival times, all the same. The service time also is the same. Now in the first case we consider the time quantum to be 2 units, and then there will be a timer interrupt and there will be preemption. And in the second case we considered one unit of time quantum for the same scenario. And if we look into the execution sequence using the NAT chart, what we find is, say this is a queue that gets formed and that gets actually considered. So this is a queue considered, and the front of the process in the front of the queue will be actually scheduled. So this is the round robin queue. Okay, so initially at time equals to 0, the trivial process is A, but after 2 units of time there will be a context switch. Okay, and in this case there will be B and A, so B will be scheduled, and then B will join the rear by the time C already got introduced before, I mean at time t equals to 4. So C came and B joined here. So this is the status of the queue. This is the front of the queue and this is the rear of the queue. Okay, so in the next time step definitely A gets scheduled, but A has got only, it has already used the CPU for 2 units of time. Its requirement is 3, so it uses just for 1 unit of time and voluntarily releases the CPU. So at time equals to 5, the status of the queue is C and B. So C automatically will be introduced like this. It will go on like this, and then C will be released after 2 time units. It will join by the time D has joined the system. So BDC, and accordingly they will be maintaining. So the queues will be maintained, and from the front of the queue things will be actually scheduled like this. So if we look into the case, the finish time can be computed, and from that the turnaround time can be computed by the difference of these two, as we found. And if we consider the mean value of the turnaround time, it turns out to be 10, and the normalized turnaround time, it turns out to be 2.52. If we repeat the same experiment with a system having a time quantum 1 unit, then you can see that, okay, so every time just 1 unit, so PA and then again PA, it continues because there is no more processes yet. And then at time t equals to 2, it has, I have not shown the queue here explicitly, you can easily figure it out. So here B came and then A is in the rear, so B will be scheduled like this. So this will be the sequence. Hopefully you can check it of your own. So if we compute the finish time, so finish time for A will be, if you scan from the rear from the end, so when you found last first occurrence of A, it is in here, so it will be 4. That's why it is 4. The finish time of B will be from the end, this is the last time the B occurred, so it will be 90, so that's why it is 90. Finish time of C will be here 70, like this. So we compute the finish time and then we compute the turnaround time by the difference of this. We found that the mean value of turnaround time, it moves up to, it increases up to 10.8 and the normalized is 2.56. Now are we getting better performance compared to the previous algorithms now, compared to SRT, SPN, HRRN? Can you recall the values? Are we getting better performance using RR? Maybe time quantum 2 or 1? This is HRRN 8 and 2.12, and this is for SPN, it is 7.6 and 1.84, and definitely this should be the best SRT because this is the ideal performance. So what we find, RR is performing, so its performance is even inferior compared to those algorithms. Now this cannot be concluded like this because this very much depends on the choice of time quantum. And if we plot for a given scenario, if we vary the time quantum like this in the x-axis, and if we perform the experiment, the so it increases then decreases, decreases like this. So the point is, the advantage of using this RR is we can skip the computation of service time, but the disadvantage is it often produces performance that is inferior that of SRT, HRR and all this, because of the choice of time quantum. So choice of time quantum, definitely you cannot change every time or multiple times in the system. So time quantum is generally fixed, and that should be fixed in such a way that it is able to work effectively in low load condition, in high load condition, when there is a mix of interactive process as well as CPU bound process, when there are just CPU bound process. So no matter what type of load is and how much the load is, the choice of time quantum should, a single choice of time quantum should work for all, and that is really a challenging factor. Okay. Another drawback is that, what is the other drawback here? You see, system processes, the IO bound processes and CPU bound processes, if you maintain round robin queue, just one queue if you maintain, so all the processes are actually getting crowded in the single queue. So unnecessarily, so based on the load of the system, who are suffering, even the system process which seems to have the I mean they should be enjoying the highest priority, they also are not getting extra benefit. So you cannot just provide them additional because you are just meant, and all time quantum and again join to the rear of the queue. So you cannot really differentiate between the processes if you maintain just one queue. So the basic modification of this is, can we maintain multiple queues just to overcome that problem, or once we note that issue, can we just take care of that? Okay, so the point is, instead of maintaining a single queue in a round robin fashion, can we maintain multiple queues? So this gives us the notion of another scheduling algorithm which is known as multi-level round robin queue scheduling. So this is again of preemptive nature because each queue is having a set of processes, and each process, once it is allocated the CPU, it will be using the CPU for a specific time quantum, not more than that. So multiple queues are maintained according to the priority. Each queue follows round robin scheduling with a time quantum, and a newly created process will be fed in any one of the queues according to its category. So this is important. And if we look into the queues, we found that there are the categorization of processes are in terms of system process, interactive editing process, batch process, student process. And as you can see that interactive editing, probably the user will wait for a while to think what to input and all. So they are given, that's why they are given lesser priority. So the processes which are system level will enjoy the highest. Interactive processes also will get a significant higher priority uh, because they will be not engaging the CPU too much because they are mostly interactive. So that's why they are given the priority. Interactive editing comes next. The batch process is typically, you can think of the CPU bound processes. So that will get the least priority, I mean almost very lower priorities, because uh, once they use it they will not release and they will again join the queue like this. So they will take multiple turns. So if I have higher priorities to these interactive processes, we can have a better throughput or at least a better response time. That is a strategy. So categorization of the processes, it is pretty intuitive, and assigning priorities to the different levels, process levels, that also is intuitive, so that it maximizes the throughput or reduces the response time like that. So here uh, when the second level queue will be processes from the second level queue will be scheduled only when none of the system level uh, process queue, I mean only if this queue is empty. I mean there are system processes but they might be all sleeping, they are all suspended, and only if these two are uh, blank or empty, only then process will be scheduled from this particular third level queue. Sorry. So what is the disadvantage of this process, of this algorithm? Deciding in the least queues when will come, because if the higher level queues are always occupied with processes. And what is the other drawback that we find? The waiting time. So here this nicely takes the advantage of RR by not computing the not requiring the computation of service time, and it differentiates between different types of processes. That is also good, but another important parameter, the waiting time, it's not taken into consideration. That's why there are many other processes which will starve, and that is not good. And that will create the problem of variance uh, in the response time, or variance in the turnaround time. So here the waiting time is not taken into consideration. So how can this be considered? So the point is we want to stick to round robin. We want to stick to formation of multiple queues, but in addition to that we would like to have the waiting time taken into consideration. So what can be the possible uh, idea to implement that? Hello, are you getting my point? So in each of these algorithm we incrementally try to make things more realistic. At the same time it should be lightweight in terms of execution and the implementation should be simple enough, and still it should be effective and uh, practically implementable. So we found that this is good, but the performance may not be, overall performance may not be good, the predictability will be high. until unless we can take care of the waiting time. So how the waiting time can be taken into consideration? Any idea? Hello? Are you getting me? Any answer? Hello? Can you hear me? Is the connection on or it has gone off? Hello?
Yes, sir, we can hear.
Okay. So I don't know whether you people are still there or not. No response is there. Anyway, so the idea is so these queues are maintained, but if we can make some provision to elevate, so if we think of like the process is here, after waiting for so long time, it got a chance to get the CPU because these levels are empty. Now once it is preempted, it wants to take a chance, so it should not. So the simple idea can be this process in the bottommost queue should not join again back to this queue, rather it can be elevated to this queue in the top level queue, because it has waited for long, so it should get the next chance a bit early. Okay, like this. And again it will then maybe if it spends, or any process, if it spends in this particular queue for one time quantum, so instead of joining the same queue level, it can descend down to the next, so it can join the rear of the next level queue. So the idea is something like we can, so if a process has been preempted in a particular queue level I, it should be forcefully it should be joining the rear of the next lower level queue, because you require more time, so you tend to be a CPU bound job, so you should be descending down and down the levels. So instead of hard coded levels, the processes are not categorized into hard categories, hard defined categories. Rather, any process like this, if it joins, it will join the top level queue. And if it preempts from this, that means it requires some more time. So if you require more time, you should go to the next lower level priority queue. And if by chance, so after this gets empty, if you again get a chance to get the CPU and you are preempted, that means you require some more time. So you tend to be a CPU bound job, so you should be pushed in the lower level or the lowest level queue, having the least priority. So if your demand is more, if you demand more CPU, so you start from the top, but you gradually descend down and down, and actually you accumulate in the bottommost level, like this. So if you do this, so you don't even have to know the type of the processes, whether they are CPU bound, IO bound, or system processes. You all give a fair or you give the equal opportunity to all the process to compete in the top level. And if they complete their execution, they will easily leave the system. If they don't, they will go down and down like this. So there is some kind of equal opportunity given, and in that process, the IO bound jobs, it will use the CPU, and it will go for IO and again come back and join here. So the IO bound jobs will be basically confined in the higher level queues, and the CPU bound jobs will gradually descend down and down, and they will be accumulating in the lower level queues. So what is not shown here is we can have a feedback from here to here. So as they descend down and down, the processes preempted from this level can be upgraded also here. So it's a kind of feedback that has been incorporated in the queuing system, in the multi-level queue. So that's why we call it as a multi-level queue, multi-level feedback round robin queue scheduling. And this is obviously preemptive type, because the under principle is following or is maintaining a time quantum, and after the time quantum is elapsed, that the process will be preempted. So multiple queues are maintained say, and instead of just 2 it can have 3 or 4, any number of levels, and higher the value of I, the lower is the priority, as you can see here. So this is I equals to 0, I equals to 1, I equals to 2, like this. The queues having now the point is one way of taking care of the waiting time is, instead of giving equal time quantum, we can have incremental time quantum in the lower levels, because here you just have I mean, you are expecting the IO bound jobs and they have not waited, so the new jobs and new processes are fed here. So almost like they have not waited for long, so that's why the time quantum is also less. But when you descend down, the time quantum in the lower level queues are much higher, in maybe in the order of 2 to the power 1 I. That means process in this last level generally will not get a chance, but if it gets a chance, it will be able to use the CPU for maybe 16 time steps, or I mean 32 time steps. Okay, so in some sense the waiting time that they have waited for long is rewarded. So this number of queues are multiple. There is a process of feedback, both feed forward and feedback, and at the same time the time quantum also can be varied in different levels. So waiting time can be taken into consideration while assigning the time quantum. So these are the different modifications that one can make, and we can see the different advantages. The hard categorization of the process level, the hard categorization of the process levels are not required. You don't have to guess how many categories they should belong to and all this, and you should not have to know about the details of the process to categorize them. So this is not possible, this is not required. And IO bound processes generally will reside in the top level, and CPU bound will be in the bottom levels, and no explicit identification of this type of the process are required, and they basically self organize themselves. So that is the nice thing that happens here. But still, what is the drawback of this strategy? So this is a strategy which, where there is no requirement of service time estimation, waiting time also is considered in some form. There is no hard categorization, so everything is it's very nice, and you don't have to make assumptions. And implementation is also very simple. There is no sophisticated calculations and all like HRRN. You don't have to compute the say the division every time for all the processes in the system. So that is time consuming. So it is typically lightweight and easy to implement also. But still, it is the disadvantage is, as you can see here, that uh, in the previous case we have differentiated. The system processes are given the highest priority, and these all interactive processes, these are all the user level processes. So you have got a clear distinction between the system level processes and the user level processes. But here you are not uh, you overcome that problem. I mean, many of these advantages you have got, but still you just try to uh, include the system level processes along with the user level processes together. You don't differentiate between them, and that can be sometimes uh, it is undesirable, because the system processes as a whole should enjoy much higher priority compared to any user level process whatsoever. Okay, so the probable solution to take care of this particular disadvantage, because we have got so many advantages, so this only drawback that is left is to probably deploy a hybrid mechanism where we have multi-level RRQ for the system processes, which has got hard categorization of these system processes, and the multi-level feedback RRQ, a separate set of queues for the this user level process. So what I mean to say is something like this. I think you can see it, that we have marked these two. So this hard categorization is meant for the system level processes, because the system level processes, the system knows what the purpose of that process is. Or when I say system level process, this means a user level process switched into the kernel mode is also considered here. So if a user level process switched to kernel mode, it is probably, it has triggered some system call. So the operating system knows what the purpose is, why it is waiting for, and what it wants to do, and all these details. So because these are known, this categorization, some kind of hard categorization is it is feasible, and it is meaningful. So the system processes, they will follow a simple multi-level RRQ, but the user processes, they still will be implemented using the this feedback based multi-level feedback RRQ scheduling, like this. Okay. So what we mean to say is the kernel assigns a CPU to a process for time quantum. This is all the same. So no matter what Q level it is. So here there is a clear distinction. There is a clear distinction between the system process and the user process. And the system processes will have, in as a whole, higher priority compared to any user level process, as you can see here. So priorities are increasing here. So this has got higher priority. In this direction. So as you can see that there is a clear distinction that no system level process will have a lower priority than any user level process. So this is guaranteed. And because we know the purpose of the system level process, we can fix the categorization and we can have simple queues. But because the user level process is not, we are not aware of what type of process it is, we still try to make it self-organized, and we have multiple queues, and we have got the feedback process. Okay. So this as a whole, it's a kind of hybrid strategy that we take to implement, and that is actually done in the Linux or Unix based system. So let us go into the details of it and see that how it works, and we'll see some examples or sample scenarios also. So here this is we'll be talking about multi-level feedback RRQ scheduling, and it's a kind of hybrid say scheduling you can think of, as we found. So these are the few points to note. Each process table entry contains a priority field used for scheduling. Okay. So in the process table entry, there are different fields. We know this is the PID. It stores the process parent PID, and there are many other values, many other fields. So one of the important field that is table entry or in the process data structure is the priority field. So this priority field is maintained or is managed in such a way that higher the value is, the lower the priority. That is the convention used in the Linux or Unix systems. If the value is more, the priority is less. So we can expect that a process will have whose value is 0 is having the highest priority. It will be scheduled immediately, like that. So every process has got an entry in the PT, and in its PT it has got one field that talks, that's a priority value of that particular process. And the range of priorities are partitioned. This is a spelling mistake. Are partitioned into two classes. One is the kernel mode priorities and the user mode priorities. Just now we mentioned. So the values are assigned in such a way that uh, you know this is a threshold priority. So the priorities assigned to the system processes will always be lesser than the threshold, and the values assigned to the user processes will always be higher than the threshold. So that's why there is a clear distinction, a boundary that exists in terms of the priorities that the system processes experience and the user processes experience. Okay. And above all, the strategy that we use here and the strategy that we use here is different, because here the priorities are, as you can see, both the classes contain several priority values, and at each level it has got a queue of process. So in each priority level there is a round robin queue. It's a queue of processes. And this threshold actually differentiate between these two. What strategy of assigning priority is followed in the system processes and what strategy is followed in the user processes, so that it actually behaves like a feedback queue. Okay. So while assigning kernel mode priorities, the kernel assigns fixed priorities to processes about to, when this kernel mode priorities need to be assigned, say for example a user process makes a system call. So if it makes a system call, then the then the process goes into the kernel mode, and then that particular user process being in the kernel mode, it will enjoy kernel mode priorities, because now it's the responsibility of the kernel to execute that system call, although it is actually it is doing the task of a user, but the user has requested, and the during that point of time it it works in the kernel mode. So in this kernel mode, as we found or as we discussed, it uses hard coded priorities. It gives hard coded priorities, and which remains unchanged. And what is the basic logic behind those assignments? The processes that, so as you can see, there are different types of process requirements or different types of requirements which makes a kernel mode process sleep. Okay, it is waiting for something to happen, and based on the reason for its sleep or suspension, this priority is assigned. What I mean is, say there are some processes which waits for the swapper means they need to get some pages from the secondary space to the primary memory frames. So the swapper say module need to be activated, so it is waiting for the swapper, so the swapper can swap, because you cannot copy two pages simultaneously from the secondary. So once this is free, then so maybe many of the pages has got a page fault, and they want the swapper process to শুধু আমি class নিচ্ছি. So they are sorry, so they are waiting for the swapper to be available, so that they can get their pages and they can continue. It may happen that some processes are waiting for the disk IO. Disk IO means they have got the buffer and they are waiting for the disk IO. And some other processes, they are waiting for the buffer itself. I mean, once they get the buffer, only then they can wait for the disk IO. But and prior to the buffer, the requirement is for the inode. Okay, inode is related to the file information. So if you can grab an inode, a free inode, only then you can request for a buffer, because through the buffer only you can write or read from the file. Okay, once you got the inode, you got the buffer, then you have to wait for the disk IO, the controller, so the controller will actually serve your request. Okay, so this is these can be the different reasons why a particular kernel mode process or a process in the kernel mode is forced to sleep, because it is waiting. Or it may be, they may be also waiting. So if I have asked for if I have executed scanf, so I am asking the user to input something, so maybe I am waiting for terminal input. Okay, I am waiting for terminal output, like this. And I think or maybe even the parent process has executed wait, so it is waiting for a child process termination. So what I mean to say is, user process, if it is in the kernel running mode, it might sleep or it might be suspended because of several reasons, and based on the reason of its suspension, its priority will be decided by the operating system. So this is intuitive to say that a process that sleeps in the low level algorithm which tends to create more bottlenecks will be given higher priority, because if a process is creating more bottlenecks, if you can assign higher priority and if you can make it happen, you will have lesser bottlenecks in the system. Okay, so among these reasons that I just explained, the reasons which probably will create more bottlenecks will be assigned higher priority, so that to avoid such bottlenecks and to ensure that throughput is increased or runs faster. So here, if you have, so who will wait for a disk IO? If somebody who has already got a buffer and already got a inode. So definitely, if you make this inode, waiting for inode, a higher priority, then the problem is, if you give, so it is waiting for the inode. So definitely, some process which is waiting for the disk, it is following this. So I mean, it's of no use, because uh, if you can rather assign this as a higher priority, this disk IO, so that process will be releasing the inode of the buffer for this or this process. Okay. So the reason for which this is waiting can be achieved if I can schedule this process. So like that. So there can be simple intuitive reasons of assigning priorities for the different events for which the processes are sleeping. Got the point? And waiting for the child, so nobody, it's asynchronous activity. So that's why such processes are given the least priority in the kernel mode, in the system processes, in the kernel mode priorities. Okay, so there are other distinctions. These are not interruptible and these are interruptible, because a terminal, whenever you press something, there is a terminal interrupt, and that says that okay, you have got your interrupt. A child exits, there is say a sick child, and it interrupts. So these are interruptible, sleeping in the interruptible mode. These are non-interruptible mode. So the idea is, as you can see here, in the kernel mode there are fixed priorities assigned based on the, but still there can be multiple processes in that same level. So like this. So this is a round robin queue in each level, and the CPU will be taking out, or the scheduler will assign us process from this level first, and if it is not, if it is empty, then only it will take a process from this level, like this. So in this order it will try to scan and find out processes, and only if the kernel level modes uh, don't have any processes ready to be executed in their queues, then only the CPU will try to schedule a user level process. Okay, but the timer or the time quantum is same for all of them. So now let us see how the user mode priorities are calculated. So till this point, is it fine? Hello, are you getting things?
Yes, sir.
Okay, so this is what I mean to say is, I mean, this is a technique, this is scheduling algorithm, which is, it's far more practical. As you can see, you can differentiate between system and the user level. You don't have to estimate anything. I mean, sorry, there will be estimations, but the estimations will be pretty straightforward. And the estimation of, or the estimation of the priority in the user mode will be explaining. I'll be explaining right now. So we'll see that it takes care of the waiting time and the service time. So this waiting time, service time is taken care of dynamically in case of user processes, but in case of system processes, you don't do that. You basically hard code them, because you know that what they are meant for. Okay, so that is how it is done. So it's basically trying to consider the concepts that the other algorithms till now used. It will try to include all those concepts together and make it a very effective and useful scheduling algorithm, and that's why it is implemented in Linux based systems. So if we look into the user mode priority calculation, we find that again the same rule holds. The lower the values, the higher the imply the higher priority, and the process priority in the user mode is calculated after every time quantum. Okay, so here, so these are one time fixed. This calculation is fixed, as we found. But in case of the user level priorities, these are recomputed every time, or periodically computed after every time quantum, because Why do you recompute? Because there is a chance that their priorities gets changed and some new process and you can find out a new process which will be scheduled. So it is based on this formula. The priority value is actually the base level user priority plus the recent CPU usage by 2. So I'll explain these two. So this base level user priority is what? This value. This value. So this may be 80, 60 or 40 or 120, whatever. So this is the value, or you can think of that this is the largest value in the kernel priority mode plus 1. Okay, the user so the system knows that how many kernel mode priorities it is maintaining. So if it is maintaining say 60 or say 70 or say 40, then the base level user priority will be 1 plus that value. That means that will enforce that any user level process will be enjoying lesser priority than all of the kernel processes, any of the kernel processes. So it will have one more parameter also, that is a recent CPU usage, and that is divided by 2. We will come to that. So what is the recent CPU usage? So somehow the system maintains the usage of the CPU usage of different processes. So how it is maintained? There is a physical clock, we all know. There is a hardware clock installed in every computing system, and that clock ticks. Ticks means the clock actually oscillates. It's a oscillator, so it basically oscillates, and per second it generates clock interrupts 50 or 60 times or maybe 80 times. So the system keeps track of time using some hardware clock that interrupts the CPU or generates clock interrupts at a fixed hardware dependent rate. Okay, what is that? Typically it is 60 to 50, 50 to 60 interrupts per second. So it's very fast, it oscillates, and accordingly it generates. So it's basically the hardware, the clock hardware that is having this provision, and from that clock there is a line that generates this interrupt line, hardware interrupt line, that passes that gets into the CPU chip. So each occurrence of a clock interrupt is called a clock tick. Okay, so that means there are 50 or 60 ticks per second, and the system clock interrupts or ticks a process several times during its time quantum. So if a particular process is running, say for example process A is running, so that process A will receive, or on behalf of the process A, the kernel will receive how many ticks? 50 ticks, say for example, or say 60 ticks it will receive, and this each of these ticks will add the CPU usage field. So the recent CPU usage field, where it is maintained? It is maintained in the process table entry. So in the process table entry you have the priority stored, and also you store the parameters based on which the priority is stored, is calculated. So it's a recent CPU usage. So recent CPU usage, what is that? There is a field. If I know that the process A is currently running, so during its time quantum, say if it is 1 second time quantum, so during the time quantum how many clock ticks or interrupts will occur? Say for example 60. So each of the tick will actually increment the recent CPU usage field of the process table entry of process A. Okay, got the point? So it will be affecting, the clock ticks will be affecting or incrementing the CPU usage field of the current running process only. This is the case, because that is using CPU. So that's why at the end of the time quantum, what do you find? That running process, the recent CPU usage has been increased by 60 ticks or by 60 units. And definitely this means what? So you are adding more to this priority, means what? You are reducing your priority. So that means in some sense, if I have used the CPU in the last time quantum, and if others are waiting, definitely I will not get the chance immediately. Okay, because in the last time quantum my CPU usage field has increased, but the others who are not running, their field has not increased. So definitely my priority will have higher value compared to others. And we'll see in one example that will not allow me to use the CPU in consecutive time steps, in consecutive time quantums, if other processes are also ready. We'll see that how it happens. Now the point is, we can see that there is a divided by 2 factor here. So divided by 2 factor is there is a decay factor. So we could have used it in this fashion only, but the point is, if the process A has used the time quantum 5 units, say 5 quantums earlier, say 5 time steps back, so it has acquired 60. Now the next time step, if it is not using the CPU usage, then it should not be penalized, it should be rather rewarded, but because you have not used the CPU. So this divided by 2 is actually decreasing that usage time factor by 2. Are you getting the point? So if you are waiting without using the CPU, your usage time that you have accumulated since your last usage will be decremented in each and every time step, and gradually with every time step, every time quantum, if you are not utilizing the CPU, your chances, your priority values will be more, because your values will be decreasing. The priority values will decrease, and in some sense your chances of getting the CPU will also increase. Got the point? So it's a dynamic process. So what we do here is, at the end of each time quantum, so during the time quantum, only the running process usage field gets affected, is incremented. But at the end of each time quantum, all the processes, irrespective of what it has done, all the processes in the process table entry, the CPU usage field is adjusted like this. They are divided by 2, and that is including the including the last running process also. So this considers a waiting time situation. Okay, this is a decay function that is used. So what is the impact of this decay function? After every time quantum during the recomputation process, all processes except the last running process, the priority values will decrease. As a result, they will move higher in the priority levels. So because of this decay, because you have decayed the usage value for all the processes, so definitely their priority values will increase. I mean, their priority values will increase. At the same time, uh, they will move up to the priority level. The chances will be more. But the process which was running, that also will be divided by 2, but it has recently used the CPU, so it will have a value higher than the remaining one. We'll see that in a example shortly. So let us see this case. So this is a time quantum 1 second, say for example, and there are say 60 ticks per time quantum in the system. And there are 3 processes: PA, process ABC. At time t equals to 0, what will be the priority values of them? As you can see the formula, base level priority and recent CPU usage by divided by 2. So what is the recent CPU usage? Recent CPU usage is 0 for all of them, because it's the initial starting point. And what is the base priority? Base priority is say for example it is set to 60. So if you add it up, it will be 60 for all. So initially 60 for all, and maybe that they have arrived. So here we are showing that ABC, A has arrived first. So it's in they have formed a round robin queue. So A is scheduled here. This is initial priority computation. Now, during that one time quantum, as you can see here, during this one time quantum, there are 60 ticks that got generated like this, ticks, and each tick has incremented the CPU usage field of the running process. So this A is the running process, but it has not impacted the CPU usage of this or this process because they are not running. So at the end of the time quantum, the process A has accumulated 60 ticks, but they have accumulated just 0 in their fields. So, and what we discussed that after the expiry of the time quantum, the priority computation will happen. This is a scheduling algorithm will run, and the first step is you compute the priorities for all the processes. So if you compute it, so this will be the 60, the base priority plus CPU usage by 2, this is 75. This becomes 60 plus 0, it is 60 plus 0. So this is 75, 60 and 60. So which will be scheduled next? The B and C both are having the same priorities now, priority values. So and definitely this one, so B and C in the same level, and A, as you can see, this has got 75. So 75 notionally what it means, it has descended down in some lower levels, user level, say this is A. So as you can see that because of the feedback process, so if you have used the CPU, you will be descending down to some levels, but you have not used the CPU, you will be elevated or you will remain the same. Okay, so now this gets scheduled. So once this gets scheduled, in the next time quantum, this process B accumulate ticks 60, C accumulates nothing, and also A accumulates nothing. So both A and C remains unchanged. And why this 30 becomes 15? Because of this, that we are dividing it by 2 every time. Okay, so this 60 became 30. Now this 30 is reduced by 2 at the end of the time step. So this 60 becomes 30 and this becomes 0 remains the same. So if you recalculate it, it will be a base priority plus 15 by 2, say base priority plus 30 by 2, base priority plus 0. Okay, and if we look into this, this means A becomes 67. So from, so now because A has not used the CPU in the last time step, as you can see here, its priority value has been decreased and it has been elevated in the higher levels. And at the same time, B, which has used the CPU in the last time step, it has been demoted in some lower levels. Okay, so A moved up and B moved down. That is how the queues are organized. So there is no, as you can see, there is no explicit queue, right? There is no explicit queue maintained, but the values of the priority maintained in the process table entry of each process will give you the notion of the queues. So C remains in the same, the base level, so it automatically gets scheduled in the next step. And again, after one tick, we can recalculate it like this, and this is a change. Now A comes in the top. So after A, B, C, again it's A's turn. So the thing is, it's basically a round robin. In a round robin fashion, they are getting the CPU, but they are not assigned in the same queue level. That is a point to note. It's not just so the system is not maintaining a single round robin queue. It is actually, it's having the provision of how many queues. So how many queues can be formed in reality, in practice? How many queues can be formed in the user level if we continue such process? Hello. What can be the values of the priorities that a process can take? Possible values. Can you hear me? Please respond. Hello? Are you getting things or? Hello? Are you all still there? Hello? Hello? May I continue the class or you all left?
Hello, sir. Yes, sir.
Don't get
You
into the
can
sleep
continue.
mode. I mean, so
Actually, no,
just
sir. I had
don't act
some
like
mic issues in my side.
suspended processes. So this becomes really difficult. So at least say something or at least respond. Sometimes it happens that you all are logged on, but you are not. So they are all logically logged on. Physically, they are not present in the class. Is that happening? I don't know. If that happens, I can take the
No, sir.
classes
Actually,
offline. I mean, it's not a problem. I can take offline classes. It will help me in managing my taking it in my own time, and I can pass on the videos. Now, are you getting things, or I mean, have you got the question? What I mean?
yes, sir.
So try to respond. My question was, how many levels of queues uh, can can be there in the user level? How many possible levels can be there? Am I going too fast, or am I not clear to you? I don't know. I mean, it becomes really difficult. I cannot see the faces also, like whether things are clear. Just tell me, are you getting things or not?
Sir, actually, we are getting, but there is a lot, so we need some time to like properly match the syllabus, sir.
Okay. So in this case, so anyway, so try to answer. So till now, what we found, can you answer? Say each process, as you can see, it starts with a base priority, right? That is this base level priority 60. This one.
Yes, sir.
Just a minute. Take a laser pointer. Okay. So this is a base level priority, and then initially it starts with 0 CPU usage. So as per the formula, so this 60 plus 0, it will be all 60. So they are all the same. That's why I have shown they are all belonging to the same level, right? So the value of the priority is associated with a particular notion of the level, this user, this priority level. Is that part clear?
Yes, sir. Yes.
So now once a particular time quantum elapsed, then there are ticks accumulated where in the currently running process. This is running process. Trivially, this is the maybe the foreground of the front process. So it accumulates 60 divided by 30, divided by 2, it becomes 30, because after the time quantum, whatever, no matter what your CPU usage is, it will be divided by 2. So it will be half, it will be half, 0 0 like this, and then the computation is performed. So again, this 60 plus 30 by 2, 60 plus 0, 60 plus 0, so that means their values become 75 60 60. So 75 60 60 means what? 75, the higher the value, as I mentioned, will be, so the lower will be the level. So 75 may be something associated here, because 60 is here, so 75 might be somewhere here, down here. So B and C having 60 will having the same level. Now which will be scheduled next? B, because in the front of it. B will accumulate the ticks in the next quantum. So that's how the value will be changed here, but they will remain unchanged here. Okay, that 15 remains here. So if I compute the priority, it will be 67. 75 means this is 60 plus 30 divided by 2, like this. Till this point, is it clear how it is changing?
Yes, sir.
So now what is the impact of this? Now A, which was earlier, you see it was 75, it got elevated because its value is now 67. So 67 is closer to 60, so it got elevated in this level. But B, whose value was earlier 60, after this time quantum, because it has used the CPU, its value will be 75. So it descended down in some level. So there is, so what I mean to say, there is no explicit queues maintained in the system. Rather, the values gives us the notion that there are different levels. So the priority values are representing priority levels, user level priorities, right? So now this C is scheduled because it is the topmost process in the queue hierarchy, queue levels. So after that, this becomes this. So because this accumulates, nobody else accumulates, so that will be the change. So as you can see, first A, B, C, then again it's a turn of the A. So actually it is a round robin kind of thing. but round robin not in a single queue. They are associated in the multiple queues. Okay, so that is how it nicely organizes. The waiting time is taken care of because of the divided by 2. The uh, the service time is taken care of because you have utilized the CPU. So everything is taken care of. So my question is, how many such levels here? How many such levels in practice may be there? If you've got too many processes and all this goes on for say 1 hour, 2 hours. So how many such levels may be there?
Sir, I think 16.
Now, why 16? That is my question. Why
Sir,
16? How
like
you
here 75 is the maximum value we are accumulating and 60 is the minimum value. So
see
what I think is
let me just tell you. Let us just assume just one process is there, just one process. Okay, process A. It starts with what priority value?
60.
60. Then it accumulates how much? 60 divided by 230. So it becomes what? 75.
75.
So with 75, if nobody is there, it will be again scheduled, right?
Yes, sir.
So if it schedules, then what will be the in the next time step? What will be its priority value?
75 plus 7.
75 plus
7.
why 7?
70. 84. 82.
Are others getting the calculation? So if A is the only process, after the first time step, it will be again uh, assign the CPU, even though its priority level is 75 because nobody else is competing with you, right? So if it uses the so with the 75, so it got scheduled. So now how much CPU time it will accumulate now? So 30 plus again 60, right? It will be, you see, it was 30. Now it would have again scheduled. So 30 again it will be accumulating 60. How much it will be the value at the end? It will be, what will be the CPU usage here?
Sir, like then 120 by 2.
So my question is, after the second time quantum, if there is only the process A, so how much CPU usage A would have accumulated? In the from the first time step it retains 30. In the second time step it accumulates another 60, right?
Yes, sir.
So it becomes how much? 90.
Total 90.
90. But 90 immediately will be divided by 2 because that is what we enforce after the time quantum. So it becomes 45,
Uh,
right? So 45 plus uh, uh, so 60 plus 45 divided by 2, that will be the answer, right?
yes, sir.
Is everybody else getting? So what will be the, so if there is only one process in this after the second time step, what will be the priority value? It will be 60 plus 45
82.
by 2, it will be 82.
82.
It will be 82. So earlier it started with 60. Now because nobody was there, it uses some CPU and it just degrades down to something like 75. From 75, in the third time quantum again it will be using sorry, it was 82. So if again gets the CPU, so what will be the value? Will it descend? I mean, will the priority value increase or decrease if this is the only process which is getting scheduled every time?
Sir, again increases.
Again it will increase, but the
45
increase
plus
will be
60,
lesser. But
105.
but the increase is lesser. I mean, increase from 60 it becomes 75, and from 75 it became 82.
75
So
plus
you can see,
80.
so it is you just have some kind of uh, non-linear kind of increase, though. So the amount of increase is decreasing in a non-linear fashion, right? So it's
Yes, sir.
like 15. So first time it will increase by 15, second time it will increase by 7, third time it will increase by 3,
3.
then 1.5, then half of that like this. So you can bound it like this. But if you have got too many processes, so my question was, how many levels will be here? How many levels will be here? So there are continuous levels like this. Okay, so it will be like 60, 61, 62. So all are the possible values, right? If you have got multiple processes, so some will jump up, some will come down and all this. So there will be many such possibilities like this. So it may not be just only 16. Are you getting the point?
Yes, sir.
So you really don't create any queues, the queue data structure, but the way things are computed, the queues are organized or the processes are organized. There is a notion of queues in which the processes are organized. So that's a nice thing that happens here. Is that part clear? So you can compute and you yourself can try to find out if there is a limit for that. So if there is a single process that keeps on running, so you can think of a series like this. So the series, will it convert to some values, or you can bound that the final value of the series. So if a process keeps using repeatedly for 100 times, definitely its priority value will increase, but it will not shoot up to 100 because it will be like, so there will be some bound. So we can figure out that. So the maximum value, maximum priority value that we can probably estimate, but the number of levels, if we think of integer levels, we can, so there will be some kind of finite number of levels. So try to assess that what can be the probable set of values.
Sir, I think we can go up to 86 or so.
Yes, so just try it. I mean, think for a while later on and try to figure it out. What may be the possible values, right? The only thing is we are not considering the decimal digits. We are considering the integer, the integer form of that priority. We are discarding the decimal points. So now after that, as you can see, the process after the process A, again the process B, again the process C will be set like that. So it's basically a round robin. You see ABC, then ABC, then ABC like this. So note the priority calculation, the decay function embeds the feedback of the wait time. So that is a nice thing. So this divided by 2 is actually the trick played in which the wait time is included. And the computation, as you can see, it's not that much. It's lightweight. So now we can probably understand that this user level processes, it uses some kind of feedback. So it is not explicitly like this, but something similar to this is happening here, and something similar to this is happening. So it's a kind of hybrid strategy, right? So this is the last slide where we say that, say, think of this situation that I am a user. So but there is a user process like user 1 and user 2, and user 1 has spawned one process, process A, and user 2 has spawned two processes, process B and C. So after all there are three processes, but two processes belong to user 2 and one process belong to user 1. Now in this case, if you use the previous technique, then what happens? Which user gets more share of CPU? If I use the same strategy of computation of priorities, so if I use it, so which user will get more share of CPU, user 1 or 2? Is the question clear? User 1 has got one process, user 2 has got two processes. So if both the users
Sir,
run
can
the
you repeat the question statement, sir?
question, I say that there are three processes, I know. Now among the three processes, one user, user 1 has created process A, and another user, say you are the user 1, you created one process, and I am the user 2, I created two processes, B and C. And the basic priority computation is all the same that I just now explained, right? So if I use the same strategy, then how they will be scheduled? ABC, 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 ABC like that. So if I run the entire system for all the processes runs for 1 hour, so how much of what amount of CPU slice will you get, and how much amount I will get overall?
Sir, like it depends on particular instance, but on an overall, second user can get more priority,
Yeah,
like
definitely
more
will get more.
CPU.
Nah, let us assume that we don't.
Yes, sir.
It's not IO bound and all this. So they're all CPU bound. They're all struggling for the CPU. That's all. So in that case, can I say that out of 1 hour, I use it because I have got two processes. I use it. I get 40 minutes of time, and you get 20 minutes of time. Can it be inferred?
Yes, sir. It will be
Yes, sir.
distributed equally, approximately.
So
Yes, sir.
the thing is now the thing is, what I mean to say is, so if I create more processes, I get more CPU share. You create less processes, you get less CPU share. Got the point? So I can again, I mean, taking into the next step. So if I know how to create fork, how to use fork and all, So I gave you, so you all of us, both of us are given with searching or say trying to find out prime numbers in a very long range. So you know how, you don't know how to create fork. You just wrote a single process for doing that, and I know how to write fork. I create two processes. So who will complete it faster? So who will be able to complete it faster? Definitely me, because I have created two processes, and after all I am getting more CPU share. That's more important point. So by creating multiple processes, I am taking more share of the CPU compared to you, what you are doing. Got the point? Are you
Yes, sir.
getting the process?
Yes, 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 sir.
Yes, sir.
Yes, sir.
Then, but that is not desired. So you should shout that why should it happen? Because in some sense, the fairness should be across users, right? The fairness should not be in the process level. Rather, the fairness should be in the user level. That is more realistic, because it's a multi-user system. There are multiple users logged in. So the system designer should ensure fairness among say users rather than individual processes. And we know that when a user is creating a process hierarchy, it generally tends to create a group of processes. Now it's not the user, what we mean is a group of processes, and every process has got a group ID, a user ID, a process ID, and the parent process ID, right? So now let us get it to this point, that a user 1 is associated with group 1. So all the processes created by user 1 is group 1. So that means group 1 has got process A and group 2 has got process B and C. Is that fine?
Yes, sir.
Now the only change that I need to make it fairer in terms of groups or users is just to have this change, small change. It is a group CPU usage. Earlier it was only this much, base priority plus recent CPU usage by 2. Now I add the group CPU usage by 2. So if I modify the formula like this, now you see what happens. So when this trivially the initial values will be 60, this CPU usage, group usage 0, so all will be 0. Now initially all are 60, so in that case, say this process A is actually scheduled. Now after the usage, I mean during the usage, during this time quantum, what values are modified? The CPU usage as well as the group usage. So group usage is another field added to the process table entry to make it fairer, right? So apart from this also is updated. So in my case, so in your case you have just one process in the entire group, so that process is running, and its CPU usage time as well as group usage time both are incremented with the ticks. And when you compute the values, it will be 60 plus the base plus this 30 by 2 and this 30 by 2. Okay, and it becomes 90. But what about these two? They have not acquired any usage here or here in both of these fields, so they will be 60-60. So which one will be the next selected? Definitely this one, or I mean this may be this or this, but let's assume this one. So now this is running. This is running means what happens? It accumulates ticks in the CPU usage because it is running, and it also accumulates, as you can see here, in its group usage. So the idea is, if process B or C, any of them is using the CPU, they are after all, so C is also getting penalized. You see, C is not using the CPU. Can you notice this here? C is not using the CPU, but C is getting penalized because its group usage field is getting accumulated, even while B is using. That is the only trick. Are you getting the point? Hello.
Yes, sir.
So that is the only trick. So the thing is, apart from CPU usage, which will be a part of your will be incremented when you are running, there will be another field which is the group usage, which will be updated when you are running, and also when some other process within your same group is also running, you have to be penalized. If this happens, so then what happens, you see, these values will be 60 plus this 15 by 2, this 15 by 2, this becomes 74. This becomes what, 60 plus 30 by 2, 30 by 2, this becomes 90. And what about this one, this becomes 75, 60 plus this 0, and this is 30 by 2. So can you look into the values here, 74, 90 and 75. So which one will be actually scheduled? Which one will be scheduled? Process. Hello.
Sir, process A, sir.
Process A. Now can you see the difference here? Because we have added the group usage field, earlier what would have happened, process A, then process B, then process C, and now what happens, process A, then B. So one from this group, one from this group, but again because of the computation in such a way that again the process A gets scheduled. So you ensure the fairness among the groups. Okay, so when this gets executed, only this CPU gets usage gets accumulated here. So now it is 90, after the third 96, 74, 67. So which gets scheduled now? Last time it was from group A, so this time it should be from group B, right? And it is happening so. And within the group B, who got scheduled prior earlier?
B.
So B.
B, and now it will be C. Are you getting the point?
Yes.
Yes,
Yes.
sir.
So the whole thing will be like the fairness. So it will be process A, B, A, C, A, B, A, C, A, B, A, C, A, B, A, C, like that. So if you see, they are having so every time one process from sorry group 1 and one process from group 2, and within the particular group they will be toggling among each other. So that is how it nicely manages the whole thing. So even if I write multiple forks, I mean multiple child processes, you know that I am not going to get any extra benefit compared to you. So now you will be being a single process also, you will get 30 minutes time, and having spawning two process also, I'll be getting 30 minutes share of time in 1 hour. Is that fine? Got the point?
Oh, yes, sir.
Yes, sir.
So
But they
that's
will
why
be
this is called,
approximately same, right? But not exact.
which one?
Like, will it be exact 30 minutes and 30 minutes?
Yes, I mean if you think of it, the time quantum is the same, na? So the number of quantums, if I think of 1 minute time, 1 second time quantum. So how many quantums you will get? You will
Okay.
get 30 quantums, and in between each 30 quantums, there is a process from the other group, either B or C. So they together will share 30 quantums. So it will,
Okay.
in terms of the quantums, it is exactly the same.
Oh,
I mean, we assume that there is no, we assume that there is no IO or anything that happens here. I mean, they are just keep on, taking their chances and preempted and all this. You got the point?
yes, sir.
So that's why this is
Yes,
called
sir.
fair share scheduling. So this fairness is in terms of the groups, the groups. So this is a sample scenario, and this is an example where we considered 1 second time quantum, base priority is 60, and here there are two groups, group 1 and 2. Group 1 is having one process like this. Okay, so CPU scheduling toggles between groups and toggles among processes within a group also, ensuring fairness. So this is something that is actually implemented in Linux or Unix based systems. So as you can see, this encompasses or utilizes all the useful concepts that we discussed in the previous algorithms. Queue, it is there. Multi-level queue, it is there. Implicit, not explicitly maintained queue. So you don't have to even maintain a queue also. Just using that formula, you can try. So this is a very elegant way of taking care of the weight, ensuring fairness, and not even knowing that how much time you require prior, and also differentiating between the system process as well as the user process. This is fine, and that's how it manages in a typical time shared environment with varying load condition. This is some scheduling which ensures a very high degree of fairness and really useful, and we all, the users, feel that okay, the system is actually running my processes no matter what others are doing. So that is the essence of the entire time sharing, the implementation of the time sharing concept, time shared multi-programming. Okay, so in the next class we will consider that how a process can change its priority, that is using the nice value in IC. So that we will consider in the next class. Okay, so is there any question?
Hello, sir.
Yes.
Actually, we needed to discuss about the scheduling of the classes. Like today, we got informed